This is the video solution to example number 1 for free body diagrams. Alright, so here's the problem we were given. We've got the 3 meters, 20 degrees, and all the other information that's up there in the text. So what's my strategy for all this? Well, to begin with, I can see that I want to know how fast the box is traveling when it reaches the bottom of the incline. To me, that suggests energy or it suggests kinematics. I'm going to go with kinematics. So my strategy starts with kinematics. But if I'm going to use kinematics and I really look at the details of what's up here, I realize I need one more variable, and that's going to be the acceleration. So to find the acceleration, I'm going to use a free body diagram. So that's where I'm really going to start. So I'm going to do it backwards. I'm going to start with my free body diagram, and then I'm going to use kinematics to find the velocity. So let's go on to the free body diagram. So here's my incline, here's my body, it's just a dot, and I got to look at my forces. First force I have is it's on the earth, so I'm going to have the pull of gravity, the weight of the object, which I'll call mg. And then I'll have a normal force perpendicular to the surface, so that's perpendicular to the surface, using the letter eta for the normal force. And then I'm going to have friction. Friction opposes motion. So the box is sliding down the incline, so that's the direction of motion. Therefore, friction is going to point up the incline. So there's my fancy F for friction. And I've got this person, Jim Shorts, he's pushing up the incline with the force as well. So he's pushing up. Unfortunately, the box is still accelerating going down. So gravity is in the direction of or parallel to the incline is a bigger force than the sum of friction and Jim Short's force. So that's going to be the net acceleration. Gravity acts on the body, the normal force of the surface acts on the body, friction acts on the body, Jim's force acts on the body. But MA does not act on the body. It's what happens when you add them all up. So MA does not touch the body, it's just hanging out on the free body diagram. So that's the first free body diagram. The second one you need to draw has to have the components. So for the second one, normal force and friction and net force and Jim's force, they're all perpendicular to each other. But the one that's not is the weight, mg. So I'll need to break that up in components using trig. So I'll make that mg the hypotenuse. I'll have mg cosine 20, and that's going to be perpendicular to the incline. And then you need to draw mg sine 20 parallel to the incline. Alright, so now I've got my second free body diagram, and I'll move it kind of out of the way so I can start summing up the forces. So I'll sum up the forces parallel and perpendicular to the net acceleration. In this case, that's going to be parallel and perpendicular to the incline to make things easy. Summing up the forces in the x direction, that's going to be the net force, and that's equal to mg sine 20, which goes in the same direction as the net force, so it has the same sign. Friction and Jim's force go the opposite direction, but parallel to the net force. Since they go the opposite direction, they're both negative. So negative friction, negative Jim's force. And that gives me the equation MA is equal to mg sine 20 minus friction minus Jim's force. In the y direction, I'm not accelerating at all, so that's going to be equal to 0. And the only two forces I have perpendicular to the incline are the normal force and mg cosine 20. So I'll say 0 is equal to the force going up minus the force going down, or the force going down minus the force going up. It doesn't matter because the negative sign just means the opposite direction. And then I'll solve that for the normal force is equal to mg cosine 20. Because I took mg and broke it up with sine and cosine, mg is no longer included in my net force expressions. Alright, so when I look at these two equations, I've got too many unknowns. I need some way of combining the equations. The way to do it when you have friction is to use the fun equation. Friction equals mu times eta. So when I use that equation, I can then replace friction with mu times eta. So there it is in red. MA is equal to mg sine 20 minus mu times Jim's force. And then what I'll do is I'll take that expression, MA is equal to mg sine 20 minus mu, and I'll replace what I got for F of y for the normal force and plug in there mg cosine 20 minus Jim's force. Now what I need to do is isolate the acceleration, so I'll divide everything by the mass. That'll isolate the acceleration, and I'm going to do one more step to make things a little bit easier on my calculator. I'm going to use the distributive property to pull the g sine 20, the g out of g sine 20, and the g out of mu cosine 20. So that becomes my new expression. Again, I'll make a little bit of room so I can use some kinematics. So now I'm switching gears, going to my kinematics. In kinematics, I've got these givens, the distance, the equation I just determined, the initial velocity is 1, and the final velocity. So if I look at the givens, I can see that I don't have time. That suggests using the equation v squared equals v naught squared plus 2ax. So I'll show you all the steps here and talk about them. In the first step, I've got the equation written down. V squared equals v naught squared plus 2ax. In the second step, I started putting in the equation. I'm not putting in numbers. That's the wrong thing to do. You don't want to solve for a. You want to use that expression because sometimes things will cancel out that'll help you. So v squared equals v naught squared plus 2, and then I've got everything in red, and all that is my expression that I just calculated for a, and all that's times x. Then I'll take the square root of everything on the right. Next step, I'll put in all my numbers and units, and then I'll do my math on the calculator. And I get the final velocity to be 2.57 meters per second. All right, so let's take this opportunity to talk about some common mistakes. First, common mistake. People will solve for a. I want you to write your final variable in terms of nothing but the variables. And that doesn't mean a number down here. It means using the actual equation for a. So up here, I don't have a number in the expression. I've got the actual equation for a in that expression up there. So I've got the variable isolated equal to nothing but variables. The only numbers I'm looking for are any angles that we have to use. Otherwise, just the variables. Another common mistake, people forget to put units next to the numbers when they do in the final step. So you want to make sure you do that. Now let's talk about the free body diagram a little bit. So with the free body diagram, the mistake here, if you look at the one in the upper left-hand corner, in the bottom right-hand corner, you can see that MA touches the body itself. MA doesn't touch the body because it doesn't act on the body. It's the result of all the other forces that act on the body. So MA shouldn't do that. It should be off way up there like it is in the top left-hand corner. So the net force doesn't touch the body. It's the sum of all the others, so it doesn't touch it. So avoid that. Let's move it away and talk about the next mistake. People draw this incomplete. See the arrows on the body? They don't actually touch the body. That's wrong. They've got to touch the body. It seems like a little thing, but it's important. So the problem here is the vectors don't touch the body, and they need to touch the body. So don't do that. So as I'm going through this, hopefully you're looking at your paper saying, did I make these mistakes? Correcting them. All right, can you see the problem here? There are no tips or arrowheads on the vectors. So you got to make sure that your vectors have arrowheads or tips on them. So don't make that mistake. Okay, let's keep going. Here's another one. Subtle mistake. Look at mg sine 20 and look at friction and look at Jim's force. They're all supposed to be parallel to each other, but mg sine 20 is parallel to the ground, not the net force and not those other forces. So that's the problem there, is it's actually drawn wrong. It's got to be parallel to the ground. So don't make that mistake either.